5.4 Wave Phenomena. Interference. Diffraction and interference are unique to waves. That is to say, only waves may perform diffraction and interference. Particles cannot. 1. Interference of waves. Interference in physics does not only mean disturbance. Interference of wave is a wave phenomena that occurs when two very similar waves overlap under certain conditions. Let's take a look at the experiment first.
We will see how water waves are interfered in different situations by using a ripple tank. Fix the two dippers about 5 centimeters apart on the bar of the vibrator. Observe the wave pattern.
In this experiment, two dippers are set into vibration by the same motor, and so they are vibrating in phase. Their waves spread and set the water into vibration. From the experiment, we can see a steady pattern of alternating lines of uniform brightness and lines of fast-changing brightness. The lines of uniform brightness correspond to lines of calm water without any vibration. And the lines of fast-changing brightness have the water surface vibrating violently, changing from a crest to a trough and then a crest, and repeats very quickly. We call the lines of calm water nodal lines, and the lines of fast-changing brightness anti-nodal lines. Together, the pattern is called interference pattern. 2. Superposition of two waves. To understand how interference is produced, we have to understand something more fundamental first.
Stretch a long spring on the floor. Flick each of the long springs sideways once at the same time in the same direction. What happens when the pulses meet each other? And what happens after the pulses have separated? Now we flick each end of the spring sideways once at the same time in opposite directions. Observe how the pulses travel along the spring. What does the resultant pulse look like when the pulses meet?
So, at the very instant when the two pulses meet, they form a resultant by vector addition. The resultant displacement is the vector sum of the displacements due to the two waves that meet at a point. So, two waves are added by the principle of superposition. Well, two crests result in a big crest. A big crest and a small trough results in a small crest. If a crest meets a trough with the same magnitude, the resultant will be nothing and zero displacement results. And after they meet, the two pulses pass each other and go straight as nothing has happened. Now we know that when two waves meet, their displacements at a point is added by the principle of superposition. A. Using phase difference. In figure 5.4e, the blue and red sets of wavelengths are due to the sources S1 and S2 respectively, and the two sources S1 and S2 are vibrating in phase. So, if S1 is now producing a crest, S2 should also be producing a crest, and more importantly, all the red and blue wavelengths are also crests. Now let's look at the point X. There are two crests meet. It should be a big crest. And after half a period, there will be two troughs at X to meet to form a big trough. At other incident, there may be a smaller displacement from S1, and it always meets with an identical displacement from S2, as S1 and S2 are in phase. Now let's look at why. There are two troughs meet. There should be the big trough, and half a period later there will be two crests at Y, and so a big crest will result. In other incident, there may be a smaller displacement from S1, and it always meets with an identical displacement from S2, as S1 and S2 are in phase. At any point like X or Y, the waves from S1 and S2 arrive in phase. The two waves reinforce each other. We say that there is a constructive interference. It results in a larger amplitude of vibration like figure 5.4h. So the brightness of the corresponding spot on the screen alternates between very bright and very dim. And of course, there is always a short time when the brightness returns to normal, when its displacement is 0. We can locate the points where the waves arrive in phase, and we can see they form lines of points where constructive interferences occur. We call these lines antinodal lines. Similarly, let's see how nodal lines are formed. Now, look at W. There's a crest from S2 and a trough from S1. The resultant is a 0 displacement. Half a period later, there's a crest from S1 and a trough from S2. The resultant is still 0. At other incident, there may be a smaller displacement from S1, and it always meets with an identical but opposite displacement from S2, as S1 and S2 are in phase. In fact, the resultant at W is always 0. We say there is a destructive interference. The case is similar at point Z. Both W and Z always remained stationary without any vibration as the waves from S1 and S2 arrive in antiphase. The displacement time graph for the particle vibration at W and Z is just a horizontal line along the time axis, as in figure 5.4k. Other points where the waves arrive in antiphase are shown, and by joining them together, we can see the lines of kind water called nodal lines, which appear as lines of uniform brightness on the screen. B. Using path difference. Well, it does not mean we have to draw two sets of circular waves to determine where constructive and destructive interference occur. We may calculate the path difference of the two waves at a point instead. The path difference at a point P is the difference of the path length from the two sources, and therefore S1P minus S2P. Let's look at figure 5.4e again. At W, the path length W, S1 equals 3.5 lambda, while W, S2 equals 5 lambda. Thus, the path difference at W equals 1.5 lambda. Similarly, we may find the path difference at X, Y, and Z easily. From the above results, we may conclude that for the point with a path difference of n plus half a lambda, there will be a destructive interference, and for the point with a path difference of n lambda, there will be a constructive interference. In fact, when the sources are in phase, a path difference of n lambda at a point ensures that the waves arrive in phase and constructive interference results. On the other hand, a path difference of n plus half a lambda ensures that the waves arrive in antiphase and destructive interference results. In example 6, determine the type of interference. You should calculate the path difference to check what kind of interference may occur at R. Try check point 5 below.